Dear students, welcome back to the series Coordination Chemistry. Here in this module, we will discuss about isomerism in coordination compounds. And so, what are isomers? Isomers are two or more compounds with the same formula but different arrangement of the atoms. So, isomers will be having same formula but the arrangement of atoms will be different. And the existence of coordination compounds with the same formula but different arrangement of ligands are isomerism in coordination chemistry. So, in coordination chemistry, isomerism will be related to the ligands, arrangement of the ligands. There will be different arrangement of the ligands. There are two types of isomerism in coordination chemistry. Broadly, they are classified as structural isomerism and stereoisomerism. Or this stereoisomerism is also called as spatial isomerism because spatial orientation is different in the stereoisomerism. So, isomerism in coordination compounds broadly classified into structural isomerism and stereoisomerism. And now, what is structural isomerism? Here the isomers that contain the same number of atoms of each kind, but they differ in which atoms are bonded to one another. Okay. So, what is the structural isomerism? The structural isomerism, the same number of atoms will be there, but the atoms will be bonded in a different manner, that is structurally different. And the structural isomers differ in their structure and bonding, that is the point that should be noted. And now, the structural isomerism, it depends upon two things. Number one is ligands that are bonded to the central metal atom or ion. Which type of ligand? What are the ligands attached to the central metal atom? And second is through which atom the ligands are being attached to the central metal atom. So, two things are to be kept in mind. The ligands which are bonded to the central metal atom, and within the ligands which atom is binding or which atom is being bound to the central metal atom. And the structural isomerism, it is further divided into different classes. Number one is ionizational isomerism. Second is hydrate isomerism, or it is also called as solvate isomerism. Third is coordination isomerism. Fourth is linkage isomerism, and fifth is coordination position isomerism. So, these different kinds of isomerism are there: ionization, hydrate, coordination, linkage and coordination position isomerism. And the stereoisomerism is further divided into two types, that is geometrical isomerism and optical isomerism. So, isomerism in coordination compounds, we have broadly they are classified into structural isomerism and stereoisomerism, and we have different 6 classes of structural isomerism, and the stereoisomerism are further divided into two types. And in the structural isomerism, first was ionization isomerism. And what is ionization isomerism? From the name itself, ionization means different ions will be provided by these isomers. While we are ionizing these compounds or this coordination compounds, different ions will be furnished. So, ionization isomerism occur when a ligand that is bound to the central metal exchanges places with an anion or neutral molecule that was originally outside the coordination complex. You know, there will be an exchange of ligands with the counter ions. So, ligands will be exchanged with the counter ions in the case of ionization isomers. See the example, CONH3 5 times ClBr, it is one complex, and now another coordination complex is CONH3 5 times BrCl. And what is the difference between these two isomers? See this, when we look into the two complexes, you can see that in this complex, the Cl is inside the coordination sphere, that is the Cl is a ligand here. In another other isomer, the ionized another isomer, it is the Cl is outside the coordination sphere. So, this Cl is being exchanged, and Here Br was outside the coordination sphere. In another next isomer, it is inside the coordination sphere. So, there is an exchange of ligands between the coordination sphere and the counter ion part. So, both these are ionization isomers. When we ionize these complexes, we will get, in this case we will get the bromide ion, that is Br minus, and in this case we will get the chloride ion. But actually when we are looking at the formula, it is same, that is CONH3 5 times Cl Br is there, again CONH3 5 times Cl and Br is there. Same but different arrangement of ligands. And the structure is given here, the structure of these complexes are given here. You can see the bromide ion is outside the coordination sphere, inside there is a chloride ion acting as a ligand, but here bromine is acting as a ligand and chloride ion is outside. The difference between the ionization isomers lies in the ions generated when each are dissolved in solution. I have already told that they will furnish different ions in solution. For example, in this case, when this complex CONH3 5 times ClBr is dissolved in water, it will give bromide ion, but when this complex CONH3 5 times BrCl is dissolved in water, we get chloride ions. So, the difference is that the difference in ions furnished in solution. Other examples of ionization isomers are given here. PTNH3 4 times Br2 Cl2 and PTNH3 4 times Cl2 Br2. What is the difference? Here in this case, chloride ion is outside, in this case chloride ion is inside. In the first example, it is bromide ion is inside the coordination sphere, in second case it is outside the coordination sphere. Different ions, spatial orientation of ligands are different in these cases. Both these are ionization isomers. Second example is CONH3 4 times Cl2NO2 and CONH3 4 times ClNO2Cl. What is the difference? See, in the first example, you can see that 4 ammonia ligands are there, 2 chloride ligands. These are acting as ligands. NO2 is outside the coordination sphere. It is not a ligand, it is just a counter ion. But in the second example, you can see that this one of the chloride ion is going to outside. One of the chloride ion, one is still inside, and to substitute that this chloride ion, which ion is moving inside? NO2. NO2 is moving inside the coordination sphere. Now, NO2 will act as a ligand here, okay, but the formula is same, so they are called as ionization isomers. Different ions, here NO2 ions will be furnished, here Cl minus ions will be furnished. And the third example, CONH3 5 times NO3 SO4 and CONH3 5 times SO4 NO3. Difference is that here sulphate SO4 2 minus ions are furnished or liberated, here NO3 minus ions are liberated. This SO4 is here inside the coordination sphere, this NO3 is outside the coordination sphere. And now, the fourth example is CONH3 5 times Br C2O4 and CONH3 5 times C2O4 Br. Again the same examples, the ions are being exchanged between the coordination sphere and the counter ion. And the final fifth example is CrNH3 5 times Br SO4 and CrNH3 5 times SO4 Br. SO4 sulphate ligand is the counter ion here, but here the sulphate ion is the ligand. Here bromide ion is the ligand, here bromide ion is the counter ion. So, that is the difference. Hope it is clear that it is clear about the ionization isomers. Ionization isomers are the isomers which are showing difference in the ions furnished in the solution, or these ions will be exchanged, or ions or neutral molecules will be exchanged between the coordination sphere and the counter ion part. And now, second type of structural isomerism, it is hydrate isomerism. It is otherwise called as solvate isomerism also. This type of isomerism result from the replacement of a coordinated group by a solvent molecule. Then that is why it is called as solvate isomerism. That is, here we are replacing a solvent molecule in the coordination sphere. When the solvent molecule is water, it is called as hydrate isomerism. If the solvent molecule is water, it is called as hydrate isomerism, or generally you can call it as solvate isomerism. Here are the examples. Here we can see water is the solvent, so H2O molecules are there. See, in the first case you can see that CrH2O 6 times Cl3. All the water molecules, 6 water molecules are ligands here. All H2O are coordinated to the metal, and the color of the complex is violet. It is a violet colored complex. But the second coordination compound is CrH2O 5 times Cl, Cl2 dot H2O. This is a water of hydration. This is not a ligand, this is not a counter ion. This is a water of hydration. So, how many water molecules are there acting as the ligand? 5, and 1 chloride, that is 1 Cl minus coordinated. The color of the complex is bluish green color, different complex, it is a different complex. But all together when we look, you can see 6 H2O molecules are there, 5 plus 1 6, and 3 chloride ions are there, but both the complexes are different. One is having a violet color, second is having a bluish green color. And the third type of complex, that is CrH2O 4 times Cl2 Cl dot 2H2O. Here 2 molecules of water act as a water of hydration, 2 molecules of water. Only 4 H2O molecules are attached or connected or bonded to the central metal atom, and 2 Cl minus ions are bonded. And this complex is having a green color. It is a different complex. But when we look all together the complexes, all are having the same formula: 6 water molecules, 3 chloride molecules, and 1 chromium atom. These are examples of hydrate isomerism. And now the third type of isomerism, third type of structural isomerism is coordination isomerism. This is observed when both cation and anion of a compound are coordination complexes. If a coordination complex contain, you have separate anionic and cationic coordination complex in a compound, it will be showing coordination isomerism. Hence, there are 2 complex compounds bound together, one with a negative charge and the other with a positive charge. And in coordination isomers, the anion and cation complexes of a coordination compound exchange one or more ligand. That is the difference. These anionic and cationic part will be exchanging the ligands with themselves. Thus, coordination isomerism arises. Here are some examples. See the complexes. The whole thing is a complex, that is CONH3 6 times, CrCN 6 times. This is an anionic part, this is a cationic part, right. So, a cationic part and anionic part arises in the same complex, and the whole thing is a coordination compound. Here see the central metal atom, we have cobalt and 6 ammonia ligands, and another central metal atom chromium 6 cyanide ligand. And now coming to the next example, CrNH3 6 times and COCN 6 times. And what are the differences between these 2 compounds? See, the cobalt is having a ligand as ammonia. See, here ammonia is acting as a ligand with the cobalt. In this case, cobalt is having cyanide ligand. The difference is that this cyanide is being exchanged with the CO, and this NH3 is being exchanged with the Cr in this case. See, CrNH3 6 times and COCN 6 times, that is the only difference. Exchange of ligands happens between the 2 metal atoms. Cobalt, in the first case, cobalt have the ligand ammonia. In the second case, cobalt is having the ligand cyanide. In the first case, chromium is having the ligand cyanide, and in second case, chromium is having the ligand ammonia. They are called the coordination isomerism. Other examples are there. CuNH3 4 times PtCl4. The whole thing is a complex. This is a coordination complex. This whole thing is a coordination complex, and this is another coordination complex. What is the difference? Here copper is having ammonia as a ligand. This platinum is having chloride as a ligand. In the second case, platinum is having ammonia as a ligand. What happens? This ammonia is exchanged with the platinum, and this chloride is exchanged with the copper. That is the only difference. So, these are the examples for coordination isomers. Again, these two are coordination isomers. How it becomes? CrNH3 6 times, COCN 6 times. In the second case, CrCN twice, NH3 4 times, and COCN 4 times, NH3 twice. What is the difference between the ligands are being exchanged with the cobalt and chromium? In this case, chromium is having ammonia as a ligand. In this case, ammonia plus cyanide ligand is there. This cyanide ligand, 6 cyanide ligands are divided as 2 and 4 in the second type. That is the only difference. So, ligands are being exchanged between the two metal ions. And this are the third example is PtNH3 4 times PtCl4 and PtClNH3 thrice PtCl3 NH3. Here the ammonia ligands, how many ammonia ligands? 4 ammonia ligands. In the second example it is only 3. 1 will be remaining with the platinum. The exchange of ammonia and chloride ligands happens between these two complexes. These are all examples for coordination isomerism. And the fourth type of isomerism, it is linkage isomerism. Linkage means link, means which atom, through which atom is linking with the central metal atom. That will be the difference. This type of isomerism is shown by the ampidentate ligand. Now, the linkage isomerism occurs with ampidentate ligands that are capable of coordinating in more than one way. I have already discussed about what is an ampidentate ligand. The ampidentate ligands are having 2 donor atoms, but only one will be bound to the central metal atom at a time. And examples are NO2 minus, ONO minus, and when it is NO2 minus, nitrogen is the coordinating atom. It is NO2 minus. This is nitro N or nitro. Simply we will call it as nitro. When it is nitro, it is through nitrogen to metal. Okay. When it is ONO, it is nitrito, or here oxygen is the donating atom. So, these are examples for ampidentate ligand. And the linkage isomers differ through which atom the molecular ligands are bound to the central ion. If the ligand is attached to the central metal atom to nitrogen, it is nitro, and in another complex it will be oxygen will be acting as the donor atom, it will be nitrito. Both are different. Here is an example, CONO2 NH3 5 times Cl2. This is an example for a coordination compound, and another coordination compound, that is COONO NH3 5 times Cl2. What is the difference in these two complexes? In the first case, it is NO2, means which is the donor atom? It is nitrogen. In the second case, in the second example, it is oxygen atom. That is the only difference. All others are same in the coordination, both the coordination compound. So, these are linkage isomers. The structure is given here, CONH3 5 times, CONH3 5 times NO2. Here nitrogen is linking with cobalt. But in the second case, CONH3, this is the same as here, but the difference is oxygen is linking with the cobalt. So, these are example for a linkage isomerism. And now, last type of structural isomerism, that is coordination position isomerism. This isomerism is shown by the bridged complexes. We have already discussed about bridge complexes and the nomenclature, etc. Here the bridge complexes exhibit this type of isomerism, and the difference is the difference is the distribution of ligands around the two metal atoms. See, the two types of bridged complexes are shown here. In this complex, in CONH3 4 times, CONH3 twice Cl2, and you have two bridged ligands, one is O2 and another is NH2. This is a complex. And now coming to the next complex, CONH3 thrice Cl, CONH3 thrice Cl, NH2 and O2. See, the bridged ligands are same. These two are same in this case, both the cases, right? And what is the difference between the two? Difference is that this is an unsymmetrical bridged complex. How it becomes an unsymmetrical? CONH3 4 times, here CONH3 twice and Cl2. There is no symmetry. See, ammonia, 4 ammonia ligands are there here in this side. Here you can see 2 ammonia ligands and 2 chloride ligands. But in this case you can see CONH3 thrice Cl means 3 ammonia molecules and 1 chloride ion is there. Here also CONH3 thrice Cl. These the ligands are same on both sides. That is why it is a symmetrical bridged complex. It is not an symmetrical, or it can be called as an unsymmetrical bridged complex. Both the complexes are different. What is the difference? The arrangement of ligands between the two groups. One is symmetrical and another is unsymmetrical. These are example for a coordination position isomerism. This type of isomerism will be shown by the bridged complexes. And now we have studied what is structural isomerism. Moving to the second broad classification, that is the stereoisomerism. What is stereoisomerism? The stereoisomerism is also called as spatial isomerism. And this type of isomerism arises from the difference in orientation of ligands around the central metal ion with respect to each other. They are further divided into geometrical isomerism and optical isomerism. And what is the difference? What is happening in stereoisomerism? There will be a difference in orientation of the ligands around the central metal atom. Orientation will be different. It will be more clear if we move through the more examples. And the first classification of stereoisomerism is geometrical isomerism. And we have studied this geometrical isomerism in organic chemistry classes, that is cis and trans. The same is there in the coordination chemistry also, cis and trans form, that is the geometrical isomerism. The metal complexes that differ only in which ligands are adjacent to one another, that is called cis, or directly across from one another, they will be called as trans. In the coordination sphere of the metal are called geometrical isomers. See the examples, it will be more clear. Example is a platinum, square planar platinum complex is given here. You can see the 2 ammonia molecules are adjacent position, are in an adjacent position, and you have 1 bromide and 1 chloride ion. If the same ligands are on the same side, if identical ligands are on the same side, it is cis isomer. As in the case of organic chemistry, the same is the situation here also. This is cis isomer, similar groups at the adjacent positions. But see the second example, ammonia ligands are opposite. See, these are in a cis position, same side. But ammonia molecules, this ammonia molecule is having here, the position is here, and the next ammonia molecule is opposite to the first ammonia. So, it is called as a trans isomer. If it is in a cis position, it is called a cis isomer. If they are in trans position, they will be trans isomer. This type of isomerism is called as geometrical isomerism. They are the most important for square planar and octahedral complexes. In this type of isomerism is mainly discussed regarding to the square planar and octahedral complexes. And first we will start with the square planar complex. The square planar complexes may be, it can be generally represented as MA4 type, MA4 type. And what is M? M is the central metal atom. See, this is M. A4 means all the atoms are same, it is A4, simply MA4 type. Is there any possibility for geometrical isomers for MA4 type? No, because all are the same ligands. Then how can we classify as cis and transform? It is impossible. So, MA4 type will not be showing any geometrical isomerism. And now coming to the next type, that is MA3B, we are actually removing, we are actually substituting one ligand with a second type B, MA3B. Is there any possibility for cis-trans isomers? No. How can it be? See the examples. MA3B, this is M, central metal atom, A, 3 and B. If I am changing the position of B, see in the second example, this B is in this position, second position. These two are actually identical, they are not different. So, if I am substituting the third position with B, it will be like this, and if I am substituting this B in the fourth position, it will be like this. On the whole, all are same, identical. So, MA3B will also show no geometrical isomerism. MA4 and MA3B will not be showing any geometrical isomerism. And now this is discussed, MA3B is discussed, and next coming to the MA2B2 type. MA2B2 means M at the center, A will be, two molecules will be similar and another two will be similar, MA2B2 type. Now have a look at that. See this, MA2B2, MA2B2. See, this A and A are in the adjacent position, they are in the adjacent position, right. Now coming to the next part, if this B is being changed, if this 2B is there in this complex, if I am changing the 2B like this and this will be same. And if this B, if I am rotating the same thing, again B and B will be coming here and B and B will be coming here. Now I have the cis, all these are cis isomers, cis. Why it is called a cis isomer? All these are cis isomers. Similar atoms are on the same side. Now coming to the other, transform. How we will call a substance, a coordination compound to be a transform? When the similar group are in the opposite position. See the example, B and B opposite, A and A opposite. It is called as a trans isomer. And if I am changing the position, here it is B, and if I am changing B and B like this, and in this case A and A like this, both are same. So these two are trans isomers, and thus we can say that MA2B2 will be showing geometrical isomerism because they exist as cis and trans form. Okay. And MA2B2, likewise MA2B2, it is the same situation is with MA2BC. It will be also showing geometrical isomerism. How it will show the geometrical isomerism? Since similar ligands, that is two similar ligands are there, A. If these two similar ligands are on the same side, I will call it as cis. And if these two similar ligands are opposite in an opposite position, I will call it as a trans isomer. The difference is that here we have identical ligand, here it is different ligand B and C. But these two forms will show similar geometrical isomerism like cis and trans form. And now coming to the third type, that is MABCD. MABCD means central metal atom and all the ligands are different, MABCD. that will be showing 3 types of isomers, geometrical isomers, and they are represented like this. And you may be thinking how it will show a geometrical isomerism. I can say these are the geometrical isomers because actually I am fixing one position. A will be fixed in all the cases. A is fixed. With respect to A, the spatial orientation is different. That is why I can say 3 geometrical isomers are there. See, A is fixed, D, C. In the first case, A will be cis to B and D and trans to C. In the second case, A is cis to C and B, it is trans to D. In the first case, it was cis to D. In the second case, it is trans to D. So, both are different. And in the third case, A is fixed as such and you have B. In these 2 cases, here and here you have B in the cis position, but in this third example you have B as a trans position. So, we have 3 types of orientation possible for M, A, B, C, D. And now, we can actually sum up what we have discussed. No geometrical isomerism is possible for MA4 and MA3B type. We have already discussed. And no geometrical isomerism are there in tetrahedral complexes also. This is very important to note. Why? Because all the 4 ligands are adjacent or equidistant to one another. See, you know that the tetrahedral complex is having a structure like this. We have the central metal and the 4 ligands are at the 4 corners of a tetrahedron. And how can it be a cis and trans position? You can't say it is a cis or trans. So, no, you can't say this is a cis isomer because these 4 are at the corners of a cube. No, this is the central metal atom and one ligand is there, one ligand is here and another ligand is here, another ligand is here. How can we say this is a cis and trans form with respect to the central metal atom? We can't say this is cis and this is trans. So, in tetrahedral complexes no such geometrical isomerism is possible for tetrahedral complexes. And now coming to the octahedral complexes. Octahedral complexes, the example, the structure of an octahedron is like this. And here also different types are there, MA6. And before moving to the MA5B type, I have to discuss about MA6. MA6 means central metal atom is M and A means ligands. How many ligands? 6 ligands. And if this is it's an octahedral structure, this is M and A, all the 6 A's are there. How can we say a cis and trans isomer possible in this case? All the positions are similar. So, in the case of A6 type, no geometrical isomerism is possible. And now coming to the next type, if we are substituting one A with B, we will get MA5B type. This is MA5B type given here, MA1, 2, 3, 4, 5 and there is one B. If I am changing the position of B, if this B is changed with here, these are similar because a regular octahedron should be viewed 3-dimensionally. Both the structure is actually similar or same. So, I can say that MA5B will not show any geometrical isomerism. No cis and trans form is possible for MA5B type. Now, coming to the next type, that is MA4B2. MA4B2 means we are substituting 2 A in MA6 with the B. So, MA4B2 means 4 molecules of A and 2 other ligand is there. Or MA4BC, if I am again substituting one B with another ligand, that is C, MA4B2 or A4BC. This is the structure. M. A4 means 1, 2, 3, 4. MA4 1, 2, 3, 4. B2 1, 2. This is the cis isomer. And now again, if I am changing this, see this B and this B, they are cis to each other. This is cis to each other. This is also cis to each other. Okay. So, both this structure is same, cis isomer. On the same side, M, this is B, 1B is here, both are on the same side. So, this is a cis isomer. In MA4B2 transform, which will be the transform? See this metal and B in this position, and in the opposite position there is another B. So, in directly opposite you can see B. This is the transform, straight opposite. This is also a straight opposite side. If this B is here and this B is here, if one B is here and one B is, suppose I am writing like this, B and B, and if I am writing A here and A, then what will be the isomer? It also will be a trans isomer, because B and B will be in the opposite, similar groups on the opposite side, again it will be a trans isomer. So, in the case of MA4B2 type, it will show cis and trans form. Cis form means similar group on the same side, these two, and the similar group on the opposite side like this. The similar situation will be with MA4BC type. BC means if this B and C, they are not similar group, but when compared to this A4, they are somewhat different. So, it can be taken as a similar group, that is, if when this B and C are like this, it will be a cis isomer, and if this B and C are like this, it will be a trans isomer. So, in the case of MA4B2 and MA4BC, that will be showing geometrical isomerism. And now coming to the next group, that is MA3B3, means 3 ligands in the octahedral complex is one type, and the three of the ligands will be of different type, that is MA3B3. They will be also showing geometrical isomerism, but in this case we will call it as FAC isomer, FAC isomer and MER isomer. You will not call as cis or trans, it will be FAC and MER. How it becomes FAC and MER? See the examples. MA3B3. In this case, all the similar groups are on the cis position. When I am comparing these three, B, this B is cis to this B is cis to this B is cis to this. But when I discuss about this complex, this B is cis to this, both these B are in a cis position, but this B is trans to this. So, we have a trans position here. So, I will call it as MER, and if all these are in a cis position, we will call as FAC, and FAC and MER in MA3B3. Again I repeat, in MA3B3 type, I can call as FAC and MER isomer according to the positioning of these ligands. If all the ligands are in the cis position, that is with respect to each other, all of them are in the cis position, I will call it as a FAC isomer. If one of them are in a trans position, I will call it as a MER isomer. Hope it is clear. And now the final type is MABCDEF, which means that all the ligands in the octahedral complexes are different, all the ligands M, A, B, C, D, E, F. They will be showing 15 geometrical isomers due to the different orientation of the ligands around M. You should remember that MABCD, which was in the square planar complexes, they showed 3 types of isomers due to this different spatial orientation of the ligands. Likewise, here also you can see the 15 geometrical isomers possible. How it is possible? The different orientation of the ligands with respect to each other, M, A, B, C, D, E, F. it is not drawn here because you have to study this the number of isomers possible only. That is why I have been drawn here. And now there are different other types also, MAA twice B2 or MAA twice BC. Then what is AA? AA means it is a bidentate ligand. For example, bidentate, I can say that it is EN was a bidentate ligand, that is ethylene diamine, means they are having 2 donor atoms. That is why it is 2 EN twice. If I write it as EN twice, then AA twice, ethylene diamine. This is MAA twice B2. AA twice means how many coordination sites will be there. One will be having 2 coordination sites, and how many such type of ligands are there? 2. So, on the whole we have 4 coordination sites plus a monodentate, 2 monodentate ligands. So, 4 plus 2, on the whole we have 6. So, it will be an octahedral complex. Again, MAA twice B2 or MAA twice BC shows cis-trans isomerism, and how they show cis-trans isomerism is shown here. See the example, it is CO EN twice. Why it is shown like this? This ethylene diamine is having 2 donor site. One ethylene diamine molecule is having 2 donor site, that is shown here, and we have how many ethylene diamine molecules here? 2. So, 1, 2, 3, 4 coordination sites are being filled, and now you have 2 chloride ion, they are the monodentate ligand. So, CO, it is CO EN twice Cl2. It is CO EN twice Cl2. See the structure, see the orientation of ligands here. Here this 2 chloride ions are in a cis position. These chloride ligands are in a cis position, though this is called a cis isomer. This is a cis isomer. And when we look at this complex, it is this chloride ions are in a trans position. It is a trans isomer, opposite side, similar groups on the opposite position. So, this type of complexes will be showing cis-trans isomerism. Again, now we can summarize this geometrical isomerism. As we know, the geometrical isomerism in cis-trans isomerism, we have generally square planar and octahedral complexes. We have discussed the possibilities of geometrical isomerism in square planar complexes, and for octahedral complexes also different types of MA6, MA5, MA, some of them were not showing and some will be showing. And finally, we have discussed about the bidentate ligands showing geometrical isomerism. Now, moving to the second type of this stereoisomerism, that is optical isomerism. What is optical isomerism? Before that, you have to understand that when the plane polarized light is passed through some coordination complexes, the plane of polarization is either rotated to right or left. Okay. When the plane polarized light is passed through some coordination complexes, these coordination complexes will be rotating the plane of polarization either to right or left. And such complexes will be existing as 2 different isomers called enantiomers. They will be called as enantiomers. And these enantiomers will be the non-superimposable mirror images. So, they are called optical isomers. Enantiomers are called optical isomers. And now, here is an example. See the example, CO Cl twice En twice, or this belong to this category, generally MAA twice A2 type. This is MAA twice A2 type. And if I take a mirror image of this complex, I will get a complex like this. This is the mirror image. Are they superimposable? No. Non-superimposable mirror images. See, when if I am fixing this complex here, will be there any symmetry, or will it be a superimposable form? No, they are non-superimposable mirror images. So, such complexes are called as enantiomers. And another example is CO En twice NH3 Cl. Here it is of type MAA twice BC, because B and C different, unidentate ligand is different. NH3 in the previous example it was same, it is in this case it is different. Again this are also example for optical isomers because they form non-superimposable mirror images. In this class we were discussing about the isomerism and different types of isomerism exhibited by the coordination complexes. What are the different criteria for exhibiting coordination complexes, isomerism for coordination complexes, etc. And in the next class we will be discussing about the stability of complexes. Thank you for watching. Bye.